So, hopefully you have tried, and if not, then I would suggest you do not start with this lecture until you have tried, but hope if you have already tested it, if you have already tried how to draw this, it will be much more useful for you this part of the lecture. So, let us start with this now, assuming that you have already tried it out. So, how would this look like? So, now without loss of generality, what I will do is start from this point. So, this will be my start. I will draw 2 vectors up, I will draw 4 vectors right, and then I will draw 4 vectors down, and then I will draw 4 vectors left. So, these two are already cancelled with respect to a perfect crystal, and the up and down have also been cancelled out. So, we have F to S, there is still a gap, and that gap, as you can see, is out of the plane, is not in the same plane as it was happening in the case of edge dislocation, and that is where it becomes very different. So, here this is the gap, and hence your Berger vector would be this. Again using the RHFS. So, finish to start, this gives us the Berger vector. So, in this particular case, what you see is that U is anti-parallel to B, and now that I have described it here, let me just go back and talk about this edge dislocation. Over here what you observed was that the Berger vector was perpendicular to U. So, this is something common, you will always realize that this is what will also distinguish between edge and screw. So, coming back to our current topic, which is the screw dislocation. So, here U is anti-parallel to B, or it will the Berger vector here will remain again, the Berger vector will remain same, only sign will change depending on the convention. So, if that is the case, it means that U will be either parallel or anti-parallel always. But it cannot be anything else. So, in general terms, U would be parallel to B. So, this is another understanding that we have. When I say parallel, it means in the sense of being in the same direction. The sense can be different, the sign can be different, that is all, that is possible depending on different convention or a different kind of screw dislocation. So, here also if you reverse the sign, if for example, if you take the U direction going into this, you can realize that you will draw this Berger vector opposite, and therefore, the Berger circuit as opposite direction, and therefore, you can start from here, finish would be here, and then finish to start, the Berger vector will also be different, or Berger vector will be in the opposite sign. So, depending on what U direction you take, you are always getting U as anti-parallel to B. So, that is also another interesting aspect. And another thing that you have to realize here is that this is called a right handed screw. What is a right handed screw? So, let us look at the screw along the axis. Now, whenever if you draw a clockwise, and if you come out of the plane, one plane, if the after drawing going through one clockwise revolution, if you come out one plane, then it is called a right handed screw. On the other hand, if you take a clockwise direction and you go one layer behind or one layer below the original plane, then it is called a left handed screw. So, right handed screw is if it advances one plane after clockwise circuit. So, the question here is it that this same screw which we are looking at is RHS from one side and LHS from other side. So, now let us imagine if you are looking, right now we have nothing to do with what is the convention, what is the line direction. All you have to worry about is the axis. So, if you are looking at this axis, then along this axis you have to see whether on rotating you are going one plane ahead or one plane back. So, from this direction we have already seen you, when you go clockwise and you came one plane ahead, then it is right handed. Now, let us imagine going looking at it from the back side. So, again from the back side you have to draw clockwise. Do not, again like I said, do not worry about the conventions, we are just trying to describe a right handed screw. So, even from the back side if you go clockwise, you can imagine that you are coming one plane ahead in that direction. So, that is still a right handed screw. In what is the bigger implication of this is that right handed screw and left handed screw are physically different. Now that I have described this, I will have to go back and talk something about positive and negative edge dislocation. So, if this is a positive edge dislocation, how will a negative edge dislocation look like? Just this. And what it would mean is that you are just rotating the crystal upside down. So, positive and negative crystal are not physically different. But right handed screw and left handed screw are physically different, and right handed screw and left handed screw can also be said as positive and negative. So, if one you are described as it is not necessarily right handed is positive, but depending on your convention, if right handed screw comes out to be positive, then the left handed side will be negative. What is this sign in your particular case? In your particular case, right handed screw is coming out to be negative. So, let us be consistent and write this as negative and this as positive. So, now we have seen the convention, we have seen two different type of dislocations. Now, what else can we understand about this? So, let us move on to understand what is called as mixed dislocation. As we will discuss later, that in reality what you have is neither a pure edge dislocation nor a pure screw dislocation, and most of the time what you will have is only a mixed dislocation. Therefore, let us see what a mixed dislocation implies. So, again let me draw this, and it will be a little bit more complicated than what we have already drawn. So, again you must follow it closely. So, we are showing over here 1, 2, 3, 4 different layers of atom, and what you would see is that when you look in this set of material, what you see is that on this side you have a edge dislocation, and when you go over here we have what we see here is what we have already described as screw dislocation. So, something like this. Let us describe the line vector like this, so that it is going in and coming out, and accordingly there is a edge dislocation and there is a screw dislocation over here. So, inside it something like this is happening. So, we have and this is the point where we are seeing screw dislocation, and this is the point where we are seeing edge dislocation. And if you look at it carefully, what you would realize is that if you have described the u like this, then the Berger vector would be, so we have to draw the anti-clockwise, and therefore, from finish to start the Berger vector would be like this. So, the Berger vector over here would also remain like this. If you go through this, you will realize that the Berger vector is still the same. And now, here you have Berger vector like this, here you have Berger vector like this. So, it seems that the Berger vector remains constant whether you are in edge dislocation or screw dislocation. It is a matter of fact that Berger vector would remain constant for one given dislocation. No matter what location you are looking at, no matter what is the orientation, the Berger vector will remain constant, which means at each of this point Berger vector is like this. However, the line direction, as you can realize, is not the same. The line direction was like this, now line direction is over here like this. And we know that u and when u and b are parallel or anti-parallel, only then it is screw. When u and b are perpendicular, only then it is edge, which means that at this point only it is edge, at this point only it is screw, and at rest of the point what is it? It is a mixed dislocation, meaning it has partially edge character, it has partially screw character, and this is what we call as mixed. The remaining portion is mixed. And we will again come back to this, but you will realize that the pure edge and pure screw are actually present only at single or basically some few points, but rest of it is mixed dislocation. Another aspect before we move on is to understand about Berger vector is that you have seen that so far the Berger vector is equal to the lattice vector, lattice translation vector. A dislocation which contains a dislocation with Berger vector equal to lattice translation vector is called a perfect or unit dislocation. As you would see that since we are describing something as perfect or unit, it means there are some dislocations which do not have perfect or unit dislocations. So, there can be imperfect dislocations or partial dislocations, but in these particular cases what we have seen so far are only perfect or unit dislocations. So, now we are in a position to talk about some important characteristics of dislocation. We have seen the fundamentals of dislocation. I would not say that we have gone thoroughly to the dislocation, but the very fundamental characteristics of the dislocations. So, what are these fundamental characteristics? Let us look at it. Important, some of these you would see that you may have not even realized, although just by the definition that we have given, these must be true for them. First and foremost, you have to realize that we saw that the dislocations are actually a line. Now, you have to realize that dislocation lines cannot start and end separately inside a point, inside a crystal. If you take a crystal, then the dislocation line cannot start arbitrarily at any point and end arbitrarily at any point. They must either form a loop or they must terminate either at a surface or a grain boundary. So, the first and most important characteristics about dislocation is that dislocation must actually lines must form a loop, or another way that it could end is it could branch into other dislocations. So, basically there are three ways that dislocations can terminate. One is either it has to come to the surface. So, the end, even the start and the finish, both of them have to come to the surface, or one of them can be at surface, the other can be in branching or start and finish can combine together to form a loop. So, these are the only three ways that the dislocation lines can end inside a crystal. Now, you would think that we have seen so many dislocation lines, the edge dislocation line and the screw dislocation line, and we saw the start point and the end point. Let us put a perfect crystal on top of it, and that what would that mean? That the dislocation start line has finished inside a crystal, but you have to think a little bit more carefully that there is extra half plane in case of edge dislocation, which would mean that the dislocation is again coming out all the way to the top of the surface on one side. So, it is still going to follow this rule that dislocation line will either form a loop or it will branch into other dislocations, or it must end at the surface. Even before I go there, so now that I have said this, which what we are explicitly saying is not possible is that it cannot, it is a corollary of what we have already said, it cannot terminate inside a crystal. You can try doing several thought experiments and you would realize that it is true, it cannot terminate inside a crystal. Another important characteristic which we have said is that line direction can change, like you saw in the case of mixed dislocation. However, when we are talking about the Berger vector you would see remains constant. We have not explicitly shown it for the mixed part, but you saw that the Berger vector for the screw component and the Berger vector of the edge component for the same line, dislocation line, remained same, and in between also we are not showing it explicitly, but that is a fact that the Berger vector would remain constant. So, the line direction may change, but Berger vector remains constant. Now, that we have already also talked about other characteristics in terms of dislocation line forming a loop, a corollary of this is also that the Berger vector must be conserved. Now, like we said, it can branch out. When it is branching out, it would mean that the total Berger vector in the three sum, whatever three or more branching that is taking place, it must remain conserved. So, we will see or we will look at it what exactly this means. So, Berger vector is conserved. We will look at it in a moment, but before that, so let us say this is one Berger vector or one dislocation line which has some particular Berger vector B. So, this is another dislocation line. So, it has branched out. So, there must be another dislocation line going like this, and I have drawn it straight. It need not be straight line, but the Berger vector would remain the same for those. So, let us say for the original one Berger vector was B1, and for the branched out the Berger vectors are like this, B2 and B3. When we say it is conserved, what we are implying is that B1 should be equal to B2 plus B3. So, although we have not drawn it to the scale over here, but this is how it should look like, B1 equal to B2 plus B3. This is what we imply by conservation of Berger vector. And again, a corollary of this is that if you take all the line direction going out from the node. So, this is your node over here. So, if you take Berger vector in a way that the line set so that all the lines are going out from it, meaning now we will describe this line vector in this direction, which would mean that the Berger vector of this will also change, and therefore, this Berger vector will become, so B1 prime would be equal to minus B1 would be equal to minus B2 plus B3, and therefore, what we have here is B1 plus B2 plus B3 equal to 0. So, no summation, or in other words Bi equal to 0. So, this is another way to represent that there is conservation of Berger vector. Over here we have assumed again some convention that the line directions have to be taken in a way that from a node all of the lines are going out. And one last important characteristic is that slip characteristics of Berger vector remains same. What we are trying to say here is that if you move from screw dislocation to edge dislocation, the type of slip that this will provide will remain same, no matter whether you are in the screw dislocation part or in the edge dislocation part, but since they have the same Berger vector, they will provide the same type of slip. In brief, what we have understood is that in general dislocation lies at some orbit angle to a Berger vector and has mixed character. At an orbit angle to u. U is the line vector and has mixed character. Another important aspect is that Berger vector will remain constant. And independent of position and orientation. So, these are the two important gist of what we have understood about dislocations so far. But this is a very broad understanding about the dislocation. We also saw that there are two different kinds of dislocation, which are the edge and the screw dislocation. So, we will see what are some of the things that we have understood about individual dislocation. So, what are the things that we have understood about individual dislocation? So, let us look at some properties. We can say that what we are looking at now is individual dislocation property. So, there are two dislocations. There will be mixed character, but in the mixed character we are in a position to resolve it into either a edge dislocation or a screw dislocation. So, from the point of view of understanding stress, strain and properties and slip, we can always resolve them into edge and screw, although we know that in true dislocation they will be always in the form of mixed dislocation. So, once you resolve it as screw dislocation and edge dislocation, then you can also say, okay, this is the characteristics it will have, which we will see over here. So, there are two dislocations, like I said, in the pure form: edge dislocation, which I am writing it like this, EL; screw dislocation, which I am writing like this, screw dislocation line. What do we know about the relation between U and B? For the edge dislocation, what did we see? U and B are perpendicular to each other. Okay, the line sense, the sense may change, positive or negative. For the screw dislocation, they are parallel. Again, sense may change, meaning it can be parallel or anti-parallel, but in broad sense it is still parallel. Slip direction. So, we have said that a Berger vector gives a good understanding about the slip direction. So, what is the slip direction? So, you would should also understand that the slip direction would change when we go from edge to screw. So, in the edge dislocation the slip direction is parallel to B. So, wherever is the Berger vector, in that direction the slip is taking place, and we know that the screw dislocation it must be different because they are it changes the direction changes, the Berger vector remains same, but the relation between Berger vector and the line direction changes. So, for example, in B and U they are parallel, in B and U in edge dislocation is perpendicular. So, the slip direction is parallel to B and in the screw dislocation it should be. So, the first hunch that you may get is that it will be perpendicular, but then you realize that no, Berger vector is constant, therefore, this will still be parallel to B. Motion of dislocation. Dislocation is not always or not all dislocations are moving in the direction of slip. This will change from certainly change from edge to screw. So, the motion of dislocation would be parallel to B for edge dislocation and perpendicular to B. So, it is the motion of dislocation which changes when we go from edge to screw, but the slip direction will remain same because B is constant and that is what defines the screw slip, and that slip will be constant or remain same as long as B is same. What can we say about the positive and negative dislocations? For edge dislocation what we saw that positive and negative the definition, it is definition dependent, there is not really much change. For this one it is actually different, physically different. So, we will close at this point with this understanding about individual dislocation property. We will get to know more about dislocations in the next class. Thank you.